Okay? That thing in front, the metal in front, needs to exchange. So our product would be
PB plus CN
okay? We've predicted the potential products. As we've predicted, we now have to make sure that we've accounted for things like charge and like phase. So let's go in and look at the charge, and we'll start with the easy one. We'll look at the zinc sulfate. Okay, did I draw zinc sulfate correctly? Okay, how would I know? We would have to do the charge. Are you required to know the charge on zinc?
Yes.
Yes, that is one you're required to memorize, and it is a +2. Are you required to know the charge on sulfate? Yes, it is -2. Is that formula correct? Yes. Okay. It is very easy to look at something and be, yes, that's correct, no, that's not. Write it out, show that work so that you can see for yourself that it's correct. Your brain can convince you that something is correct when it's not if you don't have that information written down. Okay? Did I write the formula for lead correctly?
Yes.
Yes. What is the charge on that lead?
We don't. It's got to be +2.
We absolutely do know the charge on that lead.
It's +2.
No, it is not +2. It's 0. In the single replacement reaction, we're starting with something that is a solid in its 0 charged state. When we do the single replacement, we're exchanging those things, which means the lead is going to come in at a 0 charge state. With what phase?
Solid.
Solid. We're doing the full exchange. That's the point on this. The zinc sulfate will then be what phase? Aqueous. Okay. The context of why this becomes important comes in with chapter 17. What happened to the zinc as we go from the reactant to the product? It started with a 0 charge and it ended with a +2. How do we change the charge? What things contribute to charge? All the way back to Unit 1. Protons and electrons. So if I'm now positive, maybe it's because I changed the number of protons, because if I change protons being positive, it could become more positive. What happens if I change the number of protons? I change the element. Did the element change? Nope. So I can't change the protons. What did I change? I changed the number of electrons. Okay. What did I do to the number of electrons? I lost electrons. This becomes tricky because I went from a 0 to a +2. I went up in number, and yet what happens? What's my English mathematical operator there? Subtraction, a loss. Why did I go more positive?
Because you lost negative charge.
Because electrons are negative. Remember how we talked about negative things are dangerous? We actually have a double negative here. In English, we can say don't ever use not negatives. I attempted don't not use negatives, which technically is a triple negative, or right? Okay, we can't get away with that in chemistry. Okay, we have to use the double negative. Okay, and in that use of the double negative, the end result is that I become positive. I've changed the number of electrons. Because I've changed the number of electrons, this now brings in the concept of oxidation state, which is that video you went through and watched. Right? And looking at how the electrons change, how can we name those systems? And if we look at lead, we'll notice something similar happens. Okay, what happened to the lead? It went from a +2 to a 0. How does it do that? It had to gain electrons. Because electrons don't show up in the overall equation, the electrons of loss must equal the electrons gained. They have to balance out. Okay? In most of our single replacement reactions, we don't evaluate that because that's a harder concept to deal with. We just look at, can we run the reaction? Can we predict those phases? Okay? That's the superficial start. dealing with all the gain and loss of electrons, that was that oxidation video, or the RedOX video, that you got tested on. When it comes to single replacements, because we didn't talk about how to apply single replacements, those are the questions I removed. Okay, which is really centering now on the very next question. Did that reaction happen? Okay, because in the single replacement, predictions are required. I need to be able to predict what the products are, what their phases are, but then I also have to decide, did that reaction actually occur? Okay, and usually one of the answers I get was, well, I drew a reaction, so of course it happened. Okay? If I win the lottery, I'm going to buy, the very next day, I'm going to buy one of the big fancy Tesla cars because I think they're cool. Okay? Does that mean I'm going to buy a Tesla tomorrow? No, why not? I haven't won the lottery yet. Do I have a plan for it? Yeah. Probably a bit dumb because I don't play the lottery. So having a plan for something that's never going to happen is a bit silly. Okay? But what is a chemical reaction? It's a plan. Okay? It only comes to fruition if everything actually stacks and aligns with it. How do I know that this reaction actually occurs? So looking at charges, those would balance this out to make sure that the reaction or the plan was valid, but that still doesn't mean that the plan actually happened. To run a single replacement reaction, I need another piece of data. I need an activity series. Without the activity series, I can't predict if the reaction has happened. I can predict what would happen if it did happen, but I can't actually decide that it happened. Okay? So how do I use the activity series then?
Well, you look at which one has the most activity.
We go through and look at this list. What do we notice is common for most of the things on that list? They're all metals. What is zinc?
Metal.
What is lead? What is sulfur? What is sulfur? Non-metal. Oxygen? Non-metal. So what things do I need to be looking for from my equation on this list?
Which one has more activity?
Zinc and lead. Keep it simple. The next question, I could bring in the level of activity. Okay, so I have to interpret something about what that activity series means. Okay? I wish I had a better analogy, but this is the one that's stuck in my head. Okay? The more active you are, the more likely you want to be with other things. Okay? I think Joey just got the reference. Like if you're active in the dating scene, right? The more likely you are with other people. The less active you are in the dating scene, the less likely you're with other people. Okay? So, zinc, being higher in activity, wants to be what? With other things. So we look at the chemical reaction. Where is zinc with other things?
Right side.
It's only on the right-hand side of the equation. So if I look at that chemical equation, I just think about zinc. Does zinc want that reaction to happen? Yes. Okay? Because where zinc is with other things is on the product side. That only happens if a reaction happens. Okay? So just looking at zinc and zinc being more active says reaction happens. But what if lead says otherwise? Well, that would be confusing. So let's take a look at lead. Let's see if lead actually contradicts this. Lead is less active, which means it doesn't want to be with other people. Where is lead by itself? Where is lead by itself? On the product side again. Regardless of which metal we look at, both of them are saying,
I'm happy.
make some products. Okay? They're saying the reaction occurs. Guess what happens when I mix zinc metal with lead ion? A reaction happens. Okay? And I get a transfer of electrons. What's really neat about this is we can control that transfer of electrons. Okay? We can make sure that the electrons only move where we want them to move. Say like through a copper wire. Well, that's kind of boring. Why do I want them moving through a copper wire? It's called a battery. Single replacement reactions are batteries. Okay? And if we can control how the electrons transfer from one to the other and direct that electron flow to, say, a light, we can now cause the light to turn on. Okay? If we just mix the chemicals, well, are we controlling the electron flow? No, they're just doing it on their own, which means we don't get to see anything, except maybe we form lead. Woohoo! Okay? So single replacement reactions are extremely powerful because we can control that electron flow. Okay? We don't get to really deal with or study that in this class, but that's one of the repercussions of single replacement reactions.
So what if the metal was like in the middle of the activity series? Would it just depend on the other metal?
Okay? So when we're looking at the activity series, so the question here is, what if the metal was in the middle? Okay? Would I expect a chemical reaction if I just had nickel? Yeah, just nickel. No. What do I need? Something to react with. Okay? So it's always going to be a mixture of two metals. Deciding which one is more or less active becomes then the question. Okay? And realize that when we look at this, we aren't strictly comparing zinc to lead. We're comparing zinc to lead ion. We're comparing lead to zinc ion. Okay? So it's not just I mix two metals and I saw a reaction happen. That's not the case. Okay? It's I take a metal and a metal ion and I see what happens. Okay? So try and predict those. Except for the top one. So you got 3 reactions to predict. The answers, don't freak out. We need to talk about them first. So if we go through and look at these, a couple questions popped up. So all I've gone through and done is the single replacement. I've swapped. I have not verified is anything balanced, okay, either formulas or equations. Okay? I also haven't specified any phases, and that's only because I don't like phases and I don't like dealing with it. And I'm not really asking for it at this point. Okay? So if we look at this first one, magnesium with nitrate and nickel. So all we've done is done the exchange. Usually the first question or the first thing people will do is immediately draw on a 2. And I'll ask, well, why did you do that 2 with parentheses? Because that's what that one has. Well, why does the nickel nitrate have a 2?
Because nitrate has...
To balance the nickel. Am I with nickel anymore? No. Because I am not with nickel, I don't want you putting that in there. Okay? Before you start erasing, let's finish the conversation. Okay? You need to have the right reasoning behind why you're putting stuff there. If you're just putting stuff there because it's there, that's going to lead to wrong answers. Okay? But if you have a rhetorical reason for why you want to place it there, that's a different system. Okay? And that's a different setup behind it. Okay? So why might a 2 be necessary?
Because magnesium has a charge of +2, while nitrate only has a charge of -1.
If I know the charges on those species, that's why I'm bringing those numbers in. Okay? It's to balance those charges out. Okay? So magnesium is a +2, nitrate's a -1. How do I know that? Okay? You're supposed to know it. Okay? For the magnesium, you could make an argument that you can figure it out from the periodic table. That's cool. You can do that. Okay? Or you can just straight up memorize it. For the nitrate, there's no trick. You just got to memorize it. Okay? Is it balanced? No. What is the lowest common multiple between 2 and 1? 2. How do I make a 2 into a 2? I multiply by 1. So the magnesium, there's 1 magnesium there. right? How do I make a 1 into a 2? Multiply by 2, and I could put a 2 there. That becomes confusing because that looks like NO32. Now we bring in those parentheses. And this, but you had those up there already, I know. But the reason for why they're there is now correct. Okay? And that reasoning is what drives virtually everything we do. Students and humans in general try to find patterns. You have to be careful to make sure that the pattern or the reason behind that pattern is valid. If you don't have a valid reason for finding that pattern, what you've done is lucked into an observation. You will then assume you know why you got it right, and then you get to the exam and you get it wrong and don't know why. It's because you had an invalid pattern memorized behind it. Kind of makes sense? Okay. How do you know? How would you figure that out? Once you think you found a pattern, what do you need to do?
Test it.
Test it. How many times? Okay. Probably hundreds of times. Okay. Every one of the experiments that we've talked about where we discovered atoms or neutrons or any of those things, those weren't one-off experiments. Okay. Those were hundreds, if not thousands, of repetitions behind it. Okay? So if you find a pattern that you think you want to use, that's cool. You need to test it hundreds of times. Okay? Is there a shortcut to testing it hundreds of times? A computer isn't testing it for you, and ultimately that's going to be a whole other programming issue that isn't this class. Is there a shortcut to testing that theory? Has somebody else already potentially tested that theory hundreds of thousands of times? Yeah? Who might that person be? Yeah, me. Yeah, me. Okay, that's why I'm here. You can come and be, well, I did it because of this. And I'll be like, okay, let's test that. Okay? Let me see if I can break it. Because I have more experience than you, I can break it faster than you can. Okay? If I can't break it, guess what? You've got a new system that allows you to solve it. I've got a new system that I can show students. Okay? You don't run it by me. You don't do that 100 questions of testing. Guess what happens? You hit the exam and you get it wrong. Okay? So you've got to test those theories. Okay? And we got the nickel. We could go through and draw this out, and we can now evaluate, does the reaction occur? For the reaction to occur, what do I have to do? Magnesium versus nickel. Which one's higher or lower on the activity series? Take your pick. Magnesium is higher, which means more active, which means wants to be with stuff. So I go back to my equation. Where is magnesium with stuff? On the product side. I don't have to check nickel because we verified already that that's always going to match. So guess what happens? The reaction actually occurs. Cool. What happens with the next one down below it? Okay. We've done the single replacement. Okay. Why is the 3 next to the chlorine on the reactant side? To balance the aluminum. Is the chlorine with aluminum anymore? No. So can we put the 3 there? No. Okay. How do I make sure that formula is correct? You have to know the charges for silver and for chloride. How do you know those charges? You've memorized them. When we talked about nomenclature, I don't care that you know that's called silver chloride. I do care that you know the charges behind them. Right, so when we talked about nomenclature is important for the rules behind it. The name itself, not as a big deal. Okay, in my book. Okay? So that formula is correct. Is the equation balanced? No, we can see that right away with the chlorine. Do I care at this stage?
Right now.
All I asked you to do is predict what the products are. Do we have that? Yeah. And then I asked you to predict whether it would happen. Right? So I haven't asked you to balance the equation yet, so don't worry about it. So let's take a look. What do we need to look for? Aluminum and silver. There's silver. There's aluminum. Which one do you want to look at? Okay, I heard silver. That's actually the one I wanted to do. Sorry. Silver is less active on our list, which means
It should be by itself.
it should be by itself. Where is silver by itself? On the left-hand side, or the reactant side. So if I mix silver with aluminum chloride, what is the silver going to do?
It's going to try to stay by itself.
It's going to try and stay by itself, which means, do I form products?
No.
No, this reaction doesn't happen. Okay? We'll get the exact same result with the bottom one. Okay? It's also not going to happen. Okay, so the evaluation that we've gone through and do in comparing those is exactly what you need to go through and do when trying to predict single replacement reactions. So you have to be able to look at them, identify that that's what they are, and then go through and predict them. Okay? Just kind of, never mind before I get off on tangents.
Wait, so why was the last one? Why didn't that?
Okay, because we got the question, we can look at it. If we look at the last one, we're comparing gold to copper. Which do you want to look at, copper or gold? Okay, copper is more active, which means
It's gonna want to do something.
be with something. Where is copper with something?
Well, it's on the reaction side.
On the reactant side, which means reaction doesn't happen. Kind of makes sense?
How do you write, like, how do you indicate that the reaction didn't happen? Like, what's the answer?
So what's the answer comes to a more interesting question, because it's going to come down to how is the question asked. Okay? So in this open-ended question, I asked you to predict the products and then decide, did the reaction happen? Wow, okay, so I've lost connection. That's fine. Most of my screen is erased. Yeah, it's still not working. Whatever. Okay? We're just looking at this bottom one. So deciding what would the answer be. So number one, we've got the equation written out. Okay? Just putting a line underneath it doesn't quite clearly state that that's no reaction. So how could you clearly state that that's no reaction? You could write no reaction. That would be a phenomenal way of doing that.
Scratch the whole chemical equation out.
No, and I can't draw because it's still connecting. So we'll give it some time. What I could go through and do is literally write the words, no reaction. Okay? I could erase the product here. We go back to our reaction summaries. We said there was a way we could write no reaction without writing no reaction. What could we do? NR. I could erase the product and write NR. Okay? I would argue with the single replacement, erasing the product is a bad idea. That's what allowed you to decide if the reaction happened or not. So erasing your work is generally not a good thing. Okay? On a test, that could be the conclusion that could come out of that is that you cheated. Okay? Because you copied off of somebody else. So that's not the best method, in my opinion. Okay? So what you could do is just write NR underneath it. You could write no reaction. Okay? What else could I do? If I take gold and I mix it with copper sulfate, what is found in the container? I wouldn't do it with this one because gold you don't know the charge on. A, B, C, D. All right. Another way that I could ask the question. If I mix them, what do I find in the container? Well, according to this, nothing happened, which means what do I find in the container? The exact same things that I started with. D becomes the answer. I'll get people jumping all over A, B, and C because they went through and drew out the product. Cool. But then they didn't evaluate the next step. Does the reaction happen or not? Right? The other one, because I need multiple choice answers, I could start changing the charge and balance of those formulas. Okay, why? Because it's kind of a red herring that's just going to throw you off the track. Okay? Kind of makes sense? Does that answer your question then? Okay. So I'm kind of irritated it's not connecting at all. What the hell? So, interesting observation. Notice gold is at the bottom of the activity series. Okay. Is that something we might have already predicted? If we think about all the metals, would we have expected gold, platinum, and silver to be found at the bottom of the activity series? Gold, or just print money like crazy to value their currency, because there isn't a system to support the value of that currency. Okay? Most of it is arbitrary human invention anyway. It's not like gold has this intrinsic value behind it. It's just that we decided it did.
Some cultures,
Okay.
it's called the sand dollar for a reason, and some cultures use even just shells, have used
Yeah.
just shells for currency. Seashells.
So, when it comes to the exam, you will see this again on the next exam. I give you an activity series. It's on the front of the exam. Right? Active metals, there are certain metals that react with hydrogen and water. If we look at our activity series, we do see hydrogen down there. Okay, why is hydrogen on there? It's because hydrogen is found in water. It's really the active metals that are causing this. Okay? We can see that reaction with water. Okay? Hydrogen is now our 0 point when we look at quantifying these. We don't have to quantify them in this class. If you move into 152, you do quantify them. Okay? And that quantification, the numerical value for those, comes using hydrogen as your 0 point. Okay? Some metals are so active that they'll react with the hydrogen in water, do a fancy chemical reaction, gas and bubbles, sometimes flames and explosions, okay, because they're reactive enough. Don't stress necessarily about that. It's just kind of a neat fact. Which gets us into our chapter 17, oxidation and reduction stuff. Okay? This is looking at the difference between oxidation state and charge. Okay? They are very, very similar concepts. They are so similar that I have colleagues saying, why do we even talk about oxidation state? It is charge. No, it's not. Okay? They are different things. Okay? The charge is referring to the balance of protons and electrons in anything. Okay? That can be a molecule. That can be an atom. Okay? That could be an electrical outlet. Okay? I don't really care. The oxidation state is now the balance of protons and electrons on a single atom. Okay? When we look at our compounds and our formulas, we tend to only see that atom show up maybe once or twice. So calcium shows up once here. I can look at its oxidation state. I can look at the oxygen's oxidation state. I can look at the hydrogen's oxidation state. That would give me the balance of protons and electrons for each of those elements. What if I took the balance of protons and electrons for each of those elements in that compound and I added them all together? Well, now I'd have the balance of protons and electrons for that entire compound. Also known as the charge. And I would now have the charge for that compound. Okay? So the oxidation state is specific to an atom. Charge applies to the larger unit. Okay? There are rules, of course there are, to go through and approach these. These are modified rules to deal with this. Okay? You should know the charges from your ionic compounds. Okay? Why? If I know the charge, I can determine the oxidation state, okay, which we'll see in just a second. Oxygen will always have a -2 oxidation state. Why? Okay. It's referring to its balance of protons and electrons. When I put oxygen into a system, it's always going to steal electrons from somebody else, which means it's always going to become a -2. Why would oxygen always steal electrons? Because it's more electronegative than nearly every element on the periodic table. There are 2 exceptions to Rule 2. Okay? You don't need to stress about those exceptions, but you should be able to figure out what those 2 exceptions are. When would oxygen not have a -2 oxidation state? Okay, we said it's more electronegative than whatever it's connected to. It's always stealing electrons. When would it not steal electrons? When it's bonded to fluorine. Why fluorine? Fluorine is the most electronegative. If I put oxygen next to fluorine, what happens? Fluorine steals the electrons from oxygen. Oxygen is no longer stealing electrons. Okay? The other exception, a little bit harder, but the same general idea. What happens when I bond oxygen to oxygen? Which oxygen steals the electrons? Neither. Okay? Because they have the same electronegativity, we get a different oxidation state coming out of that. Okay? 99% of the time, oxygen's going to have a -2, okay, in a compound. Okay? The sum of the oxidation numbers, and this is the big one, equals the charge on the unit. This formula should look insanely familiar. This formula should look kind of like the formula that I showed you for nomenclature. Why? Because it's the same thing. And we talked about it in nomenclature. I said it's important. You need to know it. And if you spent the time to learn it then instead of doing the moronic crossover method the textbook talks about, you now have a leg up because all you have to do is be like, oh, I wasn't actually talking about charge in the past. I was talking about the oxidation state. That's all you have to do, and you're now ready to run. Okay? If you use the crossover method, you have no concept at all of what this means, and you've got a whole nother thing to learn. This is why I tell you things, so that you simplify the work that you have to do. I know those end goals. That's why I'm calling out to them. Okay? When we dealt with nomenclature, the charge was always 0. Because in nomenclature, our compounds were always neutral charged. That was the goal. Okay? When we're dealing with oxidation state, our charge does not have to be 0. It could be anything non-zero. How would I know what that charge was? I would have to add up the oxidation states, but the oxidation states you always have to solve for. You always have to solve for how? Through that formula. To use that formula, what do you need to know? You need to know the charge. Well, if I determine the charge by adding up the oxidation states, but I determine the oxidation states by solving from the charge, I've got a bit of a problem. I need to know one or the other. The oxidation state you will always have to solve for. The charge is always given. Where's the charge given?
In the equation.
Where in the equation? The upper right-hand corner of every single compound formula, whatever you want to talk about, it is always specified in the upper right-hand corner. If you don't see a number there, that's because the number is 0. And we're lazy and we don't want to write that 0. Okay? So you always have the charge. Okay? You rarely have the oxidation state. Okay? What you're supposed to do with this is, given an equation, decide, did the oxidation states change? Well, the only way you can decide if the oxidation states change would be to do what?
Balance?
Not necessarily. I don't know what you mean by balance. I would need to determine what the oxidation states are. Okay? So, for instance, I'm holding some numbers up behind my back. Have they changed? You have no idea. Why not? Because you can't see them. When you look at the equation, does anybody see the oxidation states in the equation? No. So what do you have to do? You have to solve for them. How do you solve for them? That equation that I gave you. Okay? When you go through and solve for them, we've got them listed out here. We'll have to find the oxidation state for every single element on both sides of the equation. When I go through and do that, I've got all of these oxidation states. What happened to the oxygen? Stayed the same. So its oxidation state did not change. What happened to the iodine? It did change. It went from a +5 to a 0. How do I go down in numbers? Of course, I would add something to it. Because when I add money into my bank account goes down. No. What am I adding?
Negative.
I'm adding a negatively charged thing. We have to remember that negative sign. Okay? I'm going to add negative charge, which means my oxidation state goes down. What happened to the carbon? It went up. And again, we say, oh, well, if it went up, I have to add. No. Remember what I'm referencing. Electrons, okay, which are negative. So it has to be a loss of electrons. Okay? That in and of itself isn't horrible, except, of course, we don't like using big words like that or simple words like that, because simple words don't make us look as smart. So what do?
We use big words.
We use big words. So we invent a big word to represent the gain of electrons. Okay? The big words that we use to invent for gain of electrons is reduction. Why would we have picked the word reduction?
Because positive charge.
What happened to our oxidation state? It went from a +5 to a 0. The number was reduced. So the gain of electrons is reduction. Okay? What is the loss of electrons? Oxidation. How do we know it's oxidation? Well, when we look at the numbers, we go from a +2 to a +4, and that clearly means oxidation. Really? Okay, I don't think so either. Take a look at the carbon, reactant to product. What happened to the carbon? Just look at those structures, here to here. It gained what? Not a charge.
The carbon stays the same, you know, so you gained another oxygen.
I gained another oxygen. I increased the bonds to oxygen. You mean I oxidized? The term oxidation is coming from the reaction with oxygen. That's the origin of oxidation. The term of electrons, those are new terms. Reduction and oxidation, those are old terms. Okay? We look at this and say, well, why do we have to invent new words to describe it? We aren't inventing new words to describe it. We're using old words with new definitions. That's why both things are tied in here. You need to know those ties. Loss of electrons is oxidation. Gain of electrons is reduction. Is that a mnemonic? Okay, there we go. We have the mnemonic device Leo says Gur. If you take a biology class, they don't use Leo says Gur, which I find very odd. Leo, what is Leo?
Loss of electrons.
Fair enough. Leo is metaphorically. Well, literally. No, it is metaphorically, isn't it? A lion. Lions are animals, right? What do biologists study? Like animals and living things, right? So you would think Leo says Gur would be right up their alley. Leo, a lion. A lion's a big cat. And what a cat's... Gur. There we go. There it is. Leo says Gur. It nails it down perfectly, right up a biologist's alley. And what do they pick instead? Oxidation is loss of electrons. You mean oil rig? You mean dead things made by inorganic things getting dead things to make more dead things. Really, biologists? Is that the best you got?
Well, if they were smart, they'd be cats.
That would have been nice to be recorded. It wasn't, though. Right? Either way you memorize it, I don't care. You need to get it nailed down. I do kind of care. You should say Leo says Gur. Okay? I will still mumble that under my breath when trying to solve oxidation and reduction. Okay? It's the easiest way to keep that knowledge locked in and solve through it. You do have to go through and determine all the oxidation states, all of the gaining of electrons, the loss of electrons, all that fun stuff. Okay? What makes this worse is that you'll also see an extra little term come in here. Okay? We get the suffix
Yes.
ing and an extra word, agent. So oxidizing agent. Well, oxidizing agent sounds like oxidation. So let's read it. Oxidizing agent is the molecule that stole electrons from another compound or molecule and thereby itself was reduced. The oxidizing agent was
The carbon.
reduced. The reducing agent was oxidized. They're inverses of each other. Okay? The agent is causing something else to be oxidized. If something else gets oxidized, if I cause you to be oxidized, what has to happen to me? Well, if you're oxidized, what happened to you? You lost electrons. Where did you lose those electrons? To me. Which means I gained electrons, which means I was reduced. Okay? The agents are swapped, so you've got to be careful with those. Okay? Identify your oxidation states. Identify what was oxidized, what was reduced. Identify oxidizing agent, reducing agent. We'll pick up there on whatever the next day is, Thursday.